let's find the time complexity of insertion sort. So the algorithm sketches here. Basically what it does, as we watched from animation, is that assume that the very first element is sorted out, then beginning with the second element, compare. If that is not in right order, swap, and then third one, compare, not in right order, compare. So we keep comparing. Worst case, for each element we add more, we need to compare to the very first one. That's the worst case. If it's not in right order, compare. So the very first one, which is this one, we need to compare once, and for this one we need to compare worst case 2 times, for this one worst case 3 times, this one 4 times, and so on, so up to n minus 1 times we need to compare. So this one is a order of n square comparison is there. It is if it's worst case. Also the exchange, at each time we compare we need to exchange. So exchange also is order of n square algorithm is there. But if we use a mathematical model, recurrence relation, we can formally solve the insertion sort time complexity. So given array with n size, then if we have n minus 1 size solution, so t execution time for n is if we have n minus 1 data already sorted out, that's the execution time, then what you need to do with this element is just check each of them for the rest to find the place for this one. So we need to do check or compare or swap like n minus 1, but minus 1 is a small factor, constant factor. It does not affect the n at all. So for simplicity, we can say recurrence relationship is like this. So this is identical to the selection sort algorithm, and there we have proved that this is a order of n squared quadratic algorithm.